this computer just to try and save bandwidth, even though it's kind of a pain afterwards. Okay, well, welcome to, okay, I can't minimize Zoom. I can share my screen. Okay, so welcome to the first lecture in this course on advanced lambda calculus proofs and types. And, you know, I guess initially I sort of thought that more or less the people that are here were the ones that would take it, maybe one or two more. But we got about a dozen, I think, or even with, if you include Mike and Philip Brovchek and Philip Schlump, we got, I think 15 maybe are signed up for the class. So there's a bunch of people that are signed up for the class that maybe I didn't expect to, but I sent them some information saying what it was about, and they still signed up. So hopefully some of them will start attending, because I think it can make a difference to be here. I apologize for not initially making this a synchronous class. That probably would have been better. Then we would have had a regular scheduled time. It could be that this time conflicts for most people. So the original goal for the course was conceived as a way to get a group of graduate students working together on the understanding that sort of the background material needed to kind of understand and the very sophisticated technology that's at work in Plutus core, I should have said, which is the language being used by IOHK for doing computation on the Cardano blockchain. So probably most people here know, or maybe not, that we got, you know, a pretty good chunk of funding from IOHK and from the state, and some from the university, to set up this blockchain lab. And part of the a significant part of the reason that I was so excited about it is because they have long-term relationships with other universities, including University of Edinburgh, and they have a number of the top computer scientists working in the world in the area of functional programming languages and type theory working for IOHK now, and they put their heads together and designed a language called Core Plutus, which is the language that's being run on the actual blockchain. So you have to write programs that get compiled. The intention is that Core Plutus is not a language necessarily that anyone in their right mind would actually want to write programs in, although maybe we're going to try to do that a little bit in this class. But it's intended as a target for compilers. And yet it's very simple and expressive language. And there's a lot of theory around this language over the years, so that we kind of know it's very well characterized in terms of its behavior and and sort of system properties. So, you know, the goal, and I said was, and I probably should still say is, in case, you know, is to start students to do research in this area. So, I mean, at some point, and maybe I should try to bring up the syllabus for this thing. I don't know, do I have it on my, I may have it. In here. Yeah, so here's the syllabus for the course. And when I wrote out the syllabus, by then quite a few people had signed up, and I sort of said, okay, I maybe we'll try to make the course more general. And, we'll talk about these background things that you need to be able to understand the Plutus core material. And so, I mean, I was going to give, and we'll cover a lot. Most of this stuff will end up getting covered. But I think the strategy for the course is going to be to kind of start working our way through one or two of the Plutus core papers. And when we come across something we just don't understand, we'll back up and I'll try to give some lectures on that material. Although I should say, I don't understand all the material that's being used in, all the details about everything in Plutus core. And so certainly I can give talks, but also it could be that some of these topics are relatively self-contained that are in the Plutus core topics, and maybe we'll rotate around and try to assign people to give their own lectures on some of these topics. But roughly speaking, I think the brief discussion on model theory is kind of to characterize the difference between proof theory and model theory. In kind of classical terms, model theory is tries to essentially characterize the denotation, like a mathematical mapping from a formula to the its truth or falsity. So you want to take the formula together with information like, oh, what are the assignments of the values of the variables and so forth, and then be able to figure out whether that formula is true or false. And if we could look at that in terms of classical model theory, where you've got the full value, the full power of classical logic to use there, and the power comes mainly from the fact that for every proposition, the proposition is either true or it's false, which means you can use that to prove lots of things that you can't prove, which we'll see in constructive logics, which are actually much closer to the type theories. So, you could look at, maybe it's worth a lecture to talk about that. But it turns out that so there's kind of like these two distinctions here between that will carry throughout the course pretty much, and that is the distinction between classical logic and constructive logic. And it turns out, classical model theory is very well understood, but and so is the model theory for constructive logic, which is built on Kripke structures. So even at the propositional logic level, and or implies not, in classical model theory, we could just then take propositional variables and say, oh, they're either true or they're false. And then you can do truth table semantics. And it turns out for constructive logic, even at the propositional level, there is no finite number of values that it is enough to provide models for constructive logic. So you might think, okay, well, all right, well, maybe we need true and false and don't know. It turns out that doesn't work. Maybe we need true and false and, meaningless and don't know. It turns out that doesn't work. Any finite number of values that you might try to use to build models of propositional formulas in constructive logic does not work. You need Kripke structures, which are essentially tree structures. And I don't know that it's worth really going at all into Kripke structures. The aside here is that kind of classically, and so let's see if I can do this, is that kind of classic or, you know, I mean, in logic classically, let me just, I'm going to type a few things here since I still don't have figured out a mechanism for writing things like on a whiteboard in an interactive lecture. So I'm going to lecture one. So in kind of classical vision of logic, you've got two kinds of relations. You've got kind of like a model, and then you have this models relation for some formula, phi. So this says, you know, M models formula phi. And M is some kind of structure. It depends on what kind of logic you're doing that determines the kind of structure that you need there. And then I see my internet connection is unstable. We also, though, have things that are proofs. And the proof relation is this. So, you know, this is the models relation. And then we have this proof relation, which means that in context gamma, phi is provable. And so gamma here is kind of like some kind of data structure that keeps track of the information that we've sort of learned so far in the process of doing a proof. And then we can prove this formula phi is true by using certain proof rules. Now, it turns out that two of the most kind of big picture concepts in logic are soundness and completeness. And soundness says, okay, look. Oh, and then I should write maybe down here is that phi is true if turnstile phi, which means that for all M makes phi true, M models phi. So if every model models phi, and so this is the difference between satisfiability and a truth table. Like you can say, you know, the formula P and Q is satisfiable because if P is true and Q is true, then it's true, but it's also unsatisfiable. So it's not a valid formula. It's not a true formula, and it's not a tautology. It's not true in every model because I could make P true and Q false, and then the truth tables tell us, oh, that formula is false under that assignment. But if every model, every assignment makes a formula true, then we can write this and mean that it is a tautology or is true. So soundness, and then typically when you're starting to prove a formula, when you're just starting out to do a proof, you start the proof in the empty context. And so soundness says that for every phi, phi is true implies that phi is provable. So soundness, vertical bar, is a model or is a property really of relating the model theory to the proof system. And then completeness says for all phi, if phi is provable, I got them backwards. I apologize. Every true formula is provable, and this one is soundness. So maybe I better back up and explain. So completeness is saying every formula that's true is provable. And soundness is saying every formula that's provable is true. So these are kind of like the two biggest kind of classical questions when about logics and various kinds of logics is you take the model theory and you see how it relates to the proof theory. And, you know, for propositional logic and for first order logic, they're both sound and complete. But what Gödel showed was that in any logic that is rich enough to be able to describe arithmetic, you lose completeness. There's always some true formula. There's always some formula that's true that is not provable. And so that was Gödel's incompleteness theorem, which was probably, I think, one of the most significant results in all of science in the last century. He proved it around 1936, and it kind of ended this chase to try to like fix mathematics that Hilbert had started, because it was realized that completeness, you can't do it once you can encode arithmetic formulas in your logic. And the reason is because once you can encode arithmetic formulas is then you can use that. I'm sorry, once you can encode arithmetic, then you can use that to encode formulas themselves. And so now you have a meta language, you kind of have a circularity where you can talk about the logic in the logic, and then you lose completeness. So anyway, that's kind of all I really wanted to say about model theory. I guess I would say that you know, I think maybe after Gödel's incompleteness theorem, model theory became a little bit less important. Although Dr. Gamboa's research is in formalizing non-standard real analysis. And it turns out that a guy named Abraham Robinson found models for non-standard reals, which kind of like said, oh yes, it's just as valid to use non-standard real analysis where you have this idea of infinitesimals as it is to use the standard epsilon delta characterization of calculus. And it turns out that actually a lot of things become easier when you have infinitesimals. And he formalized that in the ACL2 theorem prover and added that material to ACL2. So that was a case where like the model theory, once you have a model, you know the axioms are consistent. If you can find a model that proves that proves all of your axioms and does not prove 0 equals 1, then you know your axioms are consistent. And that's what Robinson did, was he found a model for the axioms of non-standard model theory. Okay, so the next topic that we're going to do is we're going to talk about these Gensen proof systems, because they are kind of the standard in modern proof systems are either their natural deduction or their sequent calculus proof systems. And we're going to talk about what that means. And then we'll talk a little bit maybe about substructural, and linear logic is a kind of substructural logic. And, that could have that's kind of an important topic, but it may not bear directly on Plutus core. And of course, a major thing here is talking about the lambda calculus. And I guess I need a new line there, but we're going to talk a little bit about the untyped lambda calculus, and then about binding issues in lambda calculus, because it turns out that de Broglie indices are a way of getting rid of bound variables by just assigning kind of like the position in the formula to them. So you use kind of positions, you use integers instead of names, and then you gain a lot of power doing that. And they do de Broglie indices in Plutus core. And we'll talk about the simply typed lambda calculus, where you add types, you annotate the variables in with their types, and then you can check that you don't do something that doesn't make sense. And what you get with the simply typed lambda calculus is a language or computation system that is recursive, as opposed to general recursive. So what is general recursive versus recursive? We'll talk about that then when we get there. But I mean, general recursive means you can write programs that don't terminate. And a recursive, in a programming language that's strictly recursive, you cannot write a program that does not terminate. So simply typed lambda calculus is not Turing complete. You need to have the ability, it turns out, to write non-terminating programs to gain Turing completeness. And then we have dependently typed lambda calculus, where and in a way, I mean, the systems that we're going to be talking about, system F, is a kind of a weak dependently typed lambda calculus, because you can sort of compute at the type level. Like if you know about programming in Haskell, you've got the programming language itself, and then you've got the type language. So you've kind of got two languages. You've got the programming language and the type language. And the programming, all the programs that you write in Haskell are type checked to verify that you're not violating some type constraint. But you can't compute with types. You can only compute with terms in the computational part of the programming language. And what you can do with higher order dependent programming, type programming, is you allow computation at the type level. And then if you think about that, then there's another level above types, which are the type of types. Those are kinds. And in system F, well, system F omega, which is the basis of Plutus core, you can compute at the type level, but you can't compute higher than that. And then we're going to add recursive types. And that's one thing in Plutus core, is they've added the mu types, or the recursive types. And then it turns out there's two kinds of, or two styles, or two presentations of recursive types. And we're going to have to talk about those. And in one, two expressions in the type language, you might say they're the same. In the ISO case, they're isomorphic, and you may have to do some conversion between them, some steps of unfolding or folding a recursive definition to get from one to the other. Whereas in the equirecursive type, you just kind of make an equivalence class of all the types that are equivalent, are just kind of magically equivalent. But the problem there is that the decision problem for equirecursive types in system F omega is open. That's an open problem right now, whereas it's known for isorecursive types to how, I'm sorry, it's not the decision problem, it is a kind of decision problem, but it's the typing, the ability to run a type checker to determine, given a program in the language with isorecursive types in system F, there's an algorithm to determine if the program is well typed. If you take a program in system F omega with using equirecursive types, there's no known algorithm. So that's a result that's waiting to be shown. Either A, it's impossible, or B, here's the algorithm. Now, a lot of, I'd say virtually everything here depends on this Curry-Howard isomorphism. And I think early on, we'll do like a very concrete example of the Curry-Howard isomorphism. We'll like look at it maybe in the case of just constructive, or sometimes, I'll slip and say intuitionistic, because they kind of mean the same thing. Intuitionistic propositional logic or constructive logic or kind of propositional logic are the same things. And we could look at how propositions in, so what's a proposition? It's a formula, essentially, in constructive logic can represents a type, and then how proofs of propositions, so there's kind of like a link going, a proof is a proof of a proposition is the same as a program inhabits a particular type. So there's kind of like this relationship between formulas or propositions as types and proofs as programs. And we'll probably look at an example of that. Now, my secret goal for the class is to prepare us, or some of us, and me, for looking at building a logic where it's well known that for the Plutus core, the corresponding through the Curry-Howard isomorphism, the corresponding logic is something called second order intuitionistic logic. And it's a pretty expressive, powerful logic. And so kind of what I would like to see is a mechanism where you could write specifications for smart contracts, which are going to get translated into Plutus core, in second order, or some language that can be translated into second order intuitionistic logic. And then that is equivalent to a type in system F omega mu, the Plutus core language. And so then you would be able to turn specifications that you've written, and if you do a proof that the specification actually holds as a theorem in this logic, you get back a program which calculates the smart contract you're claiming exists. So that's kind of like the long-term goal. I don't know that I haven't talked to Phil Wadler to see if he thinks that this is an interesting idea or it's doable. But it may be pretty. It would be a tour de force to do this, and a real interesting piece of work. So I don't know. Are there any questions? That's kind of like how I'm viewing, and then of course going over Plutus core. That's how I'm viewing kind of the background material that we need to know. And there's really more to be able to understand Plutus core. So I don't know. Any questions? Any comments? Wake up there. No.
No questions. Yeah. How difficult do you think it actually is to do this?
I think
I
it's pretty
mean,
hard,
what you
but
want to do seems
but
ambitious.
it's theoretically doable, but I think it's ambitious.
Okay.
But even with that goal aside, I think knowing this material is going to be important for doing programming language work. Where, for example, if you want to compile to Plutus core, like let's say we wanted to, I don't know, build a Solidity-like programming language, but for the Cardano blockchain. Well, we design a language and we'd have to take into account the different, the UXTO model or the extended UXTO model that they use in the model of account-based model that Ethereum uses. So we'd have to take that into account, but you still could write a programming language that looks a lot like Solidity and compiles to Plutus core. And I think you need to know a pretty, significant amount about how Plutus core works to be able to make that compiler work. I don't think you can kind of do it without knowing that. So, all right, let me go back to where are my slides? Is that them? Oops, that's from yesterday's class. Okay. So, one style of doing the course would be to just start going through that material, let's say and it is a lot, it's a lot of material. I should go back to that just for a minute. I just want to say that, there are individual courses on every subtopic in here, right? I mean, you could take a course that would focus on the untyped lambda calculus. The classic text by Barendrecht is this entire, oh, did I share my screen or not? I think I forgot to share my screen. The entire topic of untyped lambda calculus is in this rather thick tome by Barendrecht, over 620 pages on untyped lambda calculus alone. There's similarly long books, well, one by Barendrecht also on the typed lambda calculus. I mean, books on model theory, there's dozens of them. Kripke structures, not so many, but there are entire books on Kripke structures. Natural deduction, sequence count. Each one of these is actually an entire course. So perhaps I'm on a fool's errand to try to bring you up to speed on all this. So my first thought was, okay, I'll spend the first half of the semester trying to go over the kind of like the big picture of each of these topics because they all play a role. And then we'll spend the second half of the semester looking at Plutus core itself. But there are a number of very good papers out on Plutus core. And last night, I read most of this one for the second time, just quickly, And I can show you that kind of in parallel with one of these other ones, because this one is programmed in Agda. And that's like, well, okay, so that's a possibility. We could all learn Agda. But here's the first paper. So this is System F in Agda for Fun and Profit. And in this paper, James Chapman, Rowan Creve, Chad Nestor, and Phil Wadler actually formalized System F. Well, they formalized more than System F. I think they formalized System F omega mu in here, and we're going to talk about what that means in a minute. But they formalized this in Agda, and Agda is a programming language / theorem proving environment, and they're able to prove properties about their formalization to show that their formalization has the properties that they expect it to. So this thing already exists out there, which is a formalization of System F omega in Agda. Now, part of my problem is that Agda notation is a little bit more difficult to read, at least for me. I mean, it could just be I need to use it and then we'd be fine. But it's a bit more difficult for me to read than, for example, this paper. Oh, come on. Why didn't you come up? I think I can click them in here and get them to come up. Where are they coming up? They're coming up somewhere. Here's a paper where they use a more standard kind of mathematical notation that you would find in these books. Oh, maybe it's not that one. It's the other one. It's Plutus core specification. And so this has the specification of the of the language. Here's the lexical grammar. Here's the grammar of the entire language. So that's also a little bit surprising, but that's kind of the point of having one of these intermediate representations like Plutus core that is a target for your compiler. The language is very small, but you've got terms, which are kind of like the programs. And then you've got types, which the terms inhabit types. And then you've got kinds, and you've only got a couple of kinds, and kinds are types have kinds. And so anyway, I don't know, I find this easier to read than the kind of idiosyncratic language notation that they use in the Agda formalization. I mean, this is all perfectly standard Agda. I mean, they oftentimes use this like backwards element of symbol. And in any case, this paper is extremely valuable because it provides not just an informal specification of language, but it provides a completely formal specification of the language, and they have proved properties about that. And it turns out that there's other technical issues that have only recently been solved. I mean, this is why this is a good course if you're interested in doing research in the area of programming languages, or especially in the area of Plutus, because I keep doing that and I don't know where it's opening. It's not. All right, let me go back here and go back here. this paper solves a problem in compiling system F when you want to have recursion. How do you compile with recursion to system F? And so this paper goes ahead and talks about that. So there's lots of interesting work, and it's all pretty cutting edge. I'm not sure, when did this paper come out? Oh, it's undated, but it's bound to be very new. Okay. Questions? I guess in a way, one of the problems with, I think, type theory and category theory is that there's a lot of jargon. There's a lot of, and what's jargon? Jargon is technical language that the people who work in the field use. They use jargon because it's technical language that allows them to speak precisely to one another. But I think it's pretty difficult for beginners to kind of get past that level of, past the jargon, to learn enough of it and sort of internalize enough of it to start to be able to puzzle out what the meaning of these things are. F mu omega mu. I mean, it looks crazy. It looks wild. What is that? Well, it's a complicated thing, is what it turns out. So I don't know. I'm thinking, before I go on, so what I'm going to do in the second hour, I'd like to talk. My thought is to kind of use the system F, Plutus, maybe use, let's say, I think I've taken to calling this SFAFFP for System F and AGDA for fun and profit. We could kind of use a combination of this paper and the Plutus core specification paper as to kind of guide what we do in the course. And what I'm going to do in the second half of the hour is kind of like go through the introduction and try to point out and discuss what are all the specific topics that need to be discussed to be able to get through this paper. There was one student who, I think I asked a bunch of you, I asked you to write down, what are your personal goals for the course? And somebody, I forget who, wrote down, my personal goal is to be able to read one of those papers and understand every line in it. And I thought, well, that's a pretty good goal. That was kind of what my goal was for the beginning of the class. And then as, we got 15 people signed up. And so anyway, I would like, the danger from me is, I really want to run this more like a graduate seminar. So we're all working together on this. And it's not like I am the font of all information here. Although I understand most of this stuff. So I can be very helpful in moving along. But I think I'm expecting kind of some of you to help push us along as well. My own danger to the course from me personally, the threat that I pose is that I tend to get stuck going like down and down and down. Like there may only be a certain amount of the material that you need to know to be able to move on with the rest of the paper. And I would, if I start pulling out, Baron-Tract and say, okay, let's start on page 1 and go through this first, we're never going to get there. And it, it may not be that extreme, but there is the danger that I'm kind of prone to sort of head that way. So I guess I would like, we've got a few more minutes before I want to take a little break in the middle of this lecture. Do you guys want to show yourselves and maybe talk a little bit about what you're thinking? I see Kyle showed up. Hi.
Hello, sorry, I can't get myself unmuted here.
Oh, there you go. So Keegan, Finley, Sujan, Kyle, what are your, Philip's an observer who has, significant interest in that topic, but he's not going to get a grade. Now, like I think I might have said, I don't know, I've said to other classes, Richard Platek, who was a pretty famous logician that taught at Cornell, and he used to say for his graduate classes, submit your homework to God, you all get an A. And, probably I'd like to just say that, but I'm not sure how he got away with it, actually. He was in the math department at Cornell, but anyway. So Kyle, what would be your preference? Do we kind of, I guess I'm sort of asking for opinions on whether we should sort of like focus more on the Plutus paper and then do, side discussions as we need them, or should we start with kind of some background material and then head to the Plutus core paper? Does anyone have a preference?
I think that some background would be nice a little bit before. I think my goal for the course is just to really just gain some understanding of like the full potential of like Lambda, and I didn't really have. It's a topic that really interested me and something that I wanted to learn more about. But aside from that, like I don't have much of an opinion on that because I have no clue.
Okay. Finn, what do you think?
I think it'd be reasonable to start with maybe more of like a really quick introduction to the Lambda calculus, because
sure,
maybe just going up as far as like what is a reduction strategy, like because
okay,
a lot of people won't have been exposed to like the very simple ideas in Lambda calculus. So understanding that, maybe working up to like a really basic example of here's what the type Lambda calculus changes,
right?
Where everything still applies, like all the basics of like term equivalence or something like that,
Okay.
Really quick intro to like the basic stuff like that. And then I think we could look at the Plutus core specification and see what they're doing to kind of encode some of that, the pieces of that language.
Okay, all right. Keegan, what do you think? Uh-oh, he fell asleep.
No, I think he might be coming. I heard him wheel over or something.
Right. Sujan, what do you think?
So, my goal here is to, I was trying to learn to write some contract on Plutus, and I thought this class helped me in that direction. That's why I decided to sign up for this one. So, if you just, as you said earlier, like if you can help us to read that Plutus specification paper and just guide us through that paper, and then, just help us, what are the topic we need to know before we can jump into that paper, and that would be
all right.
That's what I'm thinking.
Keegan, do you have any thoughts, or
yeah,
maybe
can you hear me?
Yeah, we can hear you.
Yeah, we hear you.
Okay. I agree with Finley. I would
Okay.
probably start with some of the simpler stuff in the Lambda calculus partially as
Okay.
a review or an intro.
Okay. Sure. And it's not reviewed for most people, I don't think. I mean, we never really, we did a little bit if you took, and depending on which semester, if you took functional programming, we did more or less of it. And then, you know, we talk about it some in PPL, but there really is no course on these topics, type theory and lambda calculus at UW.
And I
Philip,
guess I'm probably old enough that I predate them teaching anything at all on this subject.
yeah, well, I want to know though, what do you think in terms of strategy?
No, what Keegan and Finn said, I agree with totally. And you know, my goal out of this would be able to confidently say that I could target this kind of an environment with a simple compiler. I mean, really simple
Okay.
compiler that, you know, maybe just does a formula, but I can make it work.
Okay. All right. Well, you know, I'm going to leave the channel on. I'm just going to turn off I'm going to go get a drink and take a little break and come back in about, I don't know, is 10 minutes too much? You want to do 5? I mean, I don't need 10 minutes, but you know, we're scheduled to go from 1 to 3. All right, let's come back at, you know.
I think like 5 to 10 minutes would be fine.
All right, let's come at 5 after. That's 8, whatever, 7 minutes. 5 after. I'll see you all then.
All right.
Okay. Indicate if you're back. I see Finn, Keegan. You don't have to show me yourself, but I don't know. Isn't there a way you can just raise your hand?
I'm here.
Okay. Suzanne? Kyle?
Yeah, I'm here. I'm here.
Okay.
I'm here also.
Okay. So, I mean, what I plan to do, and I don't know if it's going to take an hour to do it, but I wanted to go through, and I put it on slides, the introduction to the, it's going to take me a little while to get that SFAFPP, System F and AGDA for Fun and Profit paper. And I did make some slides of what they, to kind of break it up. Oops. Okay. So this is from this first paper. I'm going to post these the slides up to the bio courses, and there are, even though they're not showing up, I don't know why these don't show up or display in any way as links. I'm using the href command in LaTeX to make them, but anyway, they don't. So System F is the polymorphic lambda calculus. So what that means is we're talking about typed lambda calculus. And so we're going to have to figure out, like, what does that mean? Polymorphic lambda calculus. You can see it in the term structure. It's essentially that you have, you know, in regular lambda calculus, you can take an argument that's another term. And in the polymorphic lambda calculus, you can take an argument that's a type. And so there's a type valued functions. It's pretty interesting that actually Girard and John Reynolds, who was at CMU, kind of discovered this completely independently, the same model. That's often like a good, or the same formalism or presentation. That's often a really good indicator that it's significant in some way. When two different people kind of working on slightly different areas. Girard was a computer scientist. Reynolds really was a computer scientist, and I think he died not long ago. And Girard is, as far as I know, he's still kicking, although I think he's retired. This is the book where I kind of learned a lot of this stuff, and it came out just as I started being a graduate student at Cornell. It came out in '89, and I never had a course in it there, but it really has a lot of really important material in it. And Girard's very funny. Like, he makes interesting kind of dramatic comments, which are, I don't know, well worth reading. I mean, when he's talking about the difference between model theory and proof theory, he says something like that. Well, you know, Tarski was kind of the main developer of the concept of model theory. And I mean, he did a lot of other things as well, but that was one of the main things that he did. And he says, so he's talking about the semantic traditions. One is Tarski's and the other's Hiding's, which is more proof theoretical. And he says in here, I've always loved this sentence. He says, Hiding's idea. So Hiding was the one that did the proof theory aspect and really was working from constructive logic side. Hiding's idea is less well known, but it is difficult to imagine a greater disparity between the brilliance of the original idea and the mediocrity of subsequent developments. The aim is extremely ambitious, to model not the denotations, but the proofs. And I don't know, I think, you know, it's kind of like Girardian style, um, you know, overstatement. I think actually he's wrong, because it's Hiding's, you know, modeling the proofs, and Girard's work on this has really made proof theory far more important than model theory from all of this stuff. So anyway, so polymorphic lambda calculus, they add like a lambda type operator that can take types. And they're using the propositions as types, which is a Curry-Howard thing. So under the principle of, you know, the Curry-Howard isomorphism, the arrow type, and this is simply typed lambda calculus, the arrow type of simply typed lambda calculus corresponds to implication on the logic side. And to this, system F adds a for all type. And the for all type corresponds to universal quantification over propositions. So, and you know, they say here, formalization of system F is tricky. So, you know, they're really, before this SFAFFP paper, there were a number of formalizations of system F, meaning encodings of the system in an environment like a theorem proving environment where you could prove properties about the thing. I guess I don't, let's see, that's good. So it's small but powerful. Now, this is another thing we have to look into, is these encodings. You can present a wide variety of data types, including natural numbers, lists, and trees. This was work that Church's students, who, one of them was Cleany, Stephen Cole Cleany, who was, you know, we sometimes just hear about Cleany star when you're studying formal languages. Well, I mean, he did a lot more than that. He did extremely deep studies of intuitionistic mathematics, but Cleany was a student of Church, and Rosser was a student of Church, PhD student. At the same time they were. And, you know, they encoded a lot of this early stuff, like natural numbers, lists, trees. You know, big question they had early on is, can we do subtraction? And it turns out to be a little tricky. So here's kind of the catch for why you want to go to this more rich system than system F, even though you can encode the type of list of A for any A. You can't encode what you'd like to have is you'd like to have list to take A and return, which is a type. So you'd like list to be a function from types to types. So it takes A and it returns the type of list of A. And, you know, with type classes, you kind of like in Haskell, you're kind of like stepping up a little bit into the level of being able to program with types. But in system F, they have this explicit thing. Now, the thing is that for that, you need F omega. And so system F with higher kinded types So we're going to have to study it to figure out exactly what does that mean. I mean, I sort of know what it means, but I thought that even system F omega stops at you can compute with types, but then you have kinds above and then you stop. But maybe it's because you can have types that are higher instead of just having A arrow B, you can have A arrow B arrow C or something. So we need to, I don't completely understand that. So the basic idea of system F is simple. They say, oh, and they did point out here that Girard developed system F, even though they both, system F omega, even though both Girard and Reynolds kind of identified system F as an important system. Reynolds called it the polymorphic lambda calculus and Girard called it system F. Reynolds did not move to the higher kind of types using that Girard did with system F omega. So not only does each term have a type, so you have kind of these multiple levels, but each type level object has a kind. So you introduce this new thing. You have terms, which are essentially the programs in the language, and then you have types, which are intended to characterize whether or not terms are well formed in some way. And then you have kinds, which types have kinds. So, and notably, type families are classified by higher kinds. So it says the first level relating terms and types includes an embedding of the simply typed lambda calculus plus a quantification operator. So that means terms get embedded into types using this. While the second level relating types and kinds is an isomorphic image of the simply typed lambda calculus, which means that you can do all the kinds of calculation that you can do in the simply typed lambda calculus. Excuse me. At the term level, you can do at the type level in F omega. Excuse me. I'm just going to cough for a minute. Okay, didn't want to come back on. So church encodings, like what church's students were, and PhD students were doing, was they were kind of like they took the untyped lambda calculus and they started trying to figure out, can we encode? The intention was that this could be a new foundational system for mathematics. And so they were trying to see, can we encode all these things? And they were able to encode, numbers and all of arithmetic and Boolean values and Boolean operations, like if then else. But it turns out they can represent any algebraic data type as long as it's recursive only in positive positions. Now, this business about positive positions is a very technical idea that originally comes from logic. And plays a role in these data types, and we'll have to figure out what that means. But it turns out, I don't know, like my understanding of it is relatively, I understand how to tell if something's positive or negative. And I understand that once you allow negative, once you allow recursion in a negative position, you get what are called co-inductive types. And so like, as opposed to lists are a kind of an algebraic and inductive type, streams, which are infinite lists, are co-inductive types, is a co-inductive type. So you kind of, the difference is you kind of get infinite structures, the possibility of, you get infinite structures when you plug in when you do recursion in a negative position. So we'll explore, what does that mean? Okay, so now then, Scott encoding is a different encoding technique. And, you know, their claim here is that, you know, extracting components now take constant time as opposed to time in the church encoding, time, you know, order n time to the, you know, relative to the size of the overall structure. In the Scott encoding, it takes constant time lookup. However, Scott encodings require a second system, a second extension to system F. And these are the mu type, you're adding mu types. And I don't know, variously, the system with both extensions is system F omega mu. Sometimes they started putting the mu up above the omega in later writings, I think. So terms in system F and F omega are strongly normalizing. That means that if you just start evaluating the thing, it will eventually reach a normal form. It'll reach a term that can't be evaluated anymore. There's no further evaluation. You've kind of like computed down to the bottom. So that means all programs, all the terms that you can write down in system F and all the terms, all the programs in system F omega always terminate. They will strongly normalize, meaning they will terminate. They will evaluate to a normal form that doesn't have any more computation possible in it. Now, all right, but recursive types with recursion in a negative position permit encoding of arbitrary recursive functions. So normalization of terms in system mu and system omega mu may not terminate. So something, let's see. Okay, however, so these are terms, these are programs may not terminate, but the constructs, you can also do computation at the type level, and those are strongly normalizing. This is extremely complicated technical stuff. So we need to understand why that, how that is, and what that's about. Okay, and then there are two basic approaches to recursive types. There's what I said before, there's equal recursive and there's iso-recursive. And in the equal recursive type, you can think of actually each type is not really an individual, like each piece of individual notation. So here's a piece of notation for writing down a mu type. Mu is a kind of a fixed point operator, and A is alpha, I'm sorry, is a type variable, and A is a type that may occur, in which the type variable alpha may occur free. Now, in the iso recursive types, this type is different from this type. They're not equal, but they're isomorphic, because if you unfold this type in one step, you get to this type. Or if you fold in one step, you can get from this type back to this type. And so these types are considered to be isomorphic, but there's something to do to, like, you have to actually say, oh, you know, I mean, and they could be nested, right? You could say, oh, you have to unfold at the top level and then fold this one, and then to make two typed terms in the typed language equal, you can do this folding and unfolding. And if there is a way to fold them and unfolding to make them syntactically identical, then you say, okay, they're isomorphic types. But in the equal recursive type, what you do instead is you essentially say, well, this notation here and this notation here both denote the same type. And the way to think of it is that the type is the equivalence class of all terms that are isomorphic. And then you just say, oh no, they're equal. And so you don't have really anything to prove. They're in the same equivalence class. And so this is a different kind of point of view. When you say those two things are equal, and that's because of the way that you're interpreting what a type is, and here, or in iso-recursive types, you know, each syntactic object denotes a different type, but those types can be isomorphic. Equal recursive formulations make coding easier, as it doesn't require extra forms, and we can see these in the syntax. You know, there's like an unfold and a fold operator on types that let you unfold and fold them. But it makes typing more difficult. And as I said before, it's not known whether equal recursive types for system F omega mu are decidable. And there's two references there. So I don't know, that would be an interesting thing for, you know, a PhD student maybe to look at and say, well, okay, this is kind of a burning problem. This paper only came out in 2020. There is some work done on it in these previous papers, but it's not known yet. So accordingly, Plutus core uses iso-recursive types. Yeah, Phil.
And in this context, what do you mean by decidable, as in they're actually equivalent or finitely computable?
It means if I give you two, is there an algorithm that will tell me whether or not they are the same type or not?
Okay.
So whenever you see are decidable or is decidable, that means there's a decision type procedure. And well, and maybe actually I may have just misstated actually. What you want to be able to do is take a type and take a term and see if it is in a type, and then you want to take a type and see if it's in a kind. So I'm assuming it kind of boils down to, though, being able to tell whether two arbitrary type terms, so two arbitrary terms, denote the same type. You know, you can think of this like, okay, it's like a little bit like this. It's a little bit like, you know, look, 5. Okay, 5 is one name for the number, you know, whatever S of the successor of the of 0 as a natural number. But, you know, so is 2 plus 3. And these things in the term language are kind of the same thing. Like these are different notations, but if you think of kind of the, you know, more from the model theoretic way, what do they denote? They denote an isomorphic type if you can do this unfolding or folding. But if I want to have it decidable, I have to be able to tell whether two types are equal. And so I need to be able to determine. So it would be equivalent to being able to figure out, I think, whether the two are equal. Whether two arbitrary recursive types are equal, as expressed in system F omega mu. Now, this has been something that people have had this distinction for a long time, but I guess unless you're designing a type theory, it kind of, which is what, you know, or a system like system F omega mu or Plutus core, then you have to kind of like worry about this two formulations. One is they're calling it an intrinsic formulation. And I think that this comes from I think this is Wadler's naming for them. Phil Wadler maybe named them this in a paper. I'm not sure. We could go look at this paper in a second. But one is kind of the extrinsic one is associated with Curry, Haskell Curry, and the intrinsic formulation is attributed kind of to Church. And it's sort of like, how are you going to build your type theory? And in Curry's form, the terms are described first. So like you gotta, you know, especially in a situation where we're doing computation with terms and types, it's kind of like, how do you know, terms are kind of antecedent to assigning them a type in the Curry formulation. While in a Church formulation, the type exists, and then you can talk about which terms are in that type. And so here they're going to explain why they chose a Church formulation. And one thing I would like to know that I don't know is, I think Koch may be a Curry formulation, like the theorem prover Koch, the French theorem prover Koch, chicken or rooster, might be I think it's a Curry formulation, whereas like New Pearl was a Church formulation. So it could be, I mean, you know, all right, I'm getting recorded saying this, but I mean, I think there could be like a distinction being made here between like kind of like more of a EU style and American style of presenting type systems. Okay, and now this is a you know, an interesting, but maybe even like a side issue, but except that I would have thought it's a side issue. But so one of the biggest problems, and you know, if you did that reading from Harper's book, how do you deal with bound variable names is a huge, complicated issue, because capture avoiding substitution is just brutal to try to reason about. And so that's what's happening when you do beta reduction. We'll talk about that. Well, maybe we'll even get to talk a little bit about it today. But so capture avoiding, so, you know, I got a friend named Shankar who only goes by Shankar. I always found that interesting. From SRI, who's a computer scientist at SRI. And he did his PhD at UT Austin with Boyer and Moore in the ACL2 group, but before it was ACL2. And he said, okay, I'm going to do for my PhD thesis, I'm going to prove Gödel's incompleteness theorem in the Boyer-Moore theorem prover. And he worked on it for like a few years, and it was like failing. He couldn't do it. And then he changed his variable naming mechanism from being, you know, bound variables like the kind that Harper presented, although there are methods to work with them that are a little bit better, then to De Broglie indices. And all of a sudden, he was able to prove that everything went through. And I think that's kind of like the largest early example. I'm not even sure that, when would that have been? Like 1988? I don't know when Shankar did his thesis. But at the time, that was one of the largest formalizations of a major logic theorem in a theorem prover, and he had to use De Broglie indices. And so instead of using names, you just kind of use pointers. Wherever the variable occurred, you say, how many binders do I have to go up in the tree to find the one that bound me? But you can imagine that now when you like strip a binder off, all of a sudden variables that were previously off the top of a syntax tree, variables that were previously bound may be free now. Or if you add another binder on top, now you've got to adjust you got to adjust the indices depending on where they occur in the tree. And so they're saying here, you know, computing De Broglie indices, it eases formalization, but requires error-prone arithmetic to move a term underneath a lambda expression. And so, I mean, we'll program it. It's not that hard, but I mean, you know, little things like that can be tricky, and it's an easy point to make an error in an implementation. But their point seems to be here that the reason to choose a church-style formalization is because an intrinsic formalization catches such errors because they would lead to incorrect types. So the types come first, and you would have an error and the terms get built after the types. So the final, like, you know, upshot of this whole discussion is that they use an intrinsic formulation, which means that types are kind of formulated, and then we figure out, like, then we can build the terms that occur in a type, and they're going to use De Broglie indices. So I don't know, I mean, hopefully, you know, I realize that, again, it's like a lot of jargon, but I'm hoping my description is giving you some picture of maybe we don't understand all the details. And I don't know why the intrinsic formulation works better with you. I guess I don't know why they're claiming the intrinsic formulation catches such errors. They're claiming it. I don't really see it, but it was helpful to them in the formalization. So I don't understand all the details, but I'm hoping it's giving you like at least some kind of rough understanding of the kinds of issues that they were grappling with when they decided how to build their system. So I don't know, let me stop sharing for a minute and see, or I don't know, you could just talk. Does anyone have any thoughts? This is a lot of stuff to do in one semester to build up enough knowledge to be able to understand this paper in detail. Questions, comments? Okay. Well, I'm thinking all of a sudden that, like, I don't know, we have, Philip, you got something?
No, go ahead.
Okay. I'm thinking that, let's see. Kind of the easiest way maybe to talk about the lambda calculus is to, this is the whole, basically, this is the whole untyped lambda calculus in Haskell. And I can kind of maybe make a little file here where I'm going to like sort of like write it down a little bit more. So remember that when we're encoding these things in Haskell, what we're doing is we're encoding the language. And I don't know, I think Barendrecht would say, capital lambda, I don't know, what does he say? Capital lambda, the language of lambdas are either X, where X is a variable. So this is a syntactic description. Or it's an application of the form M applied to N, where M and N are in lambda. I don't know. I could write it. I mean, maybe this is bad. I should just write capital lambda instead of trying to simulate it. Or it's a term that looks like, and you have to pick something here for denoting lambda. I mean, really, so we can say / lambda x, and then there's a dot, and then there's an M. So this is actually the entire syntax of lambda calculus. And, maybe here I say, just saying that M and M are in lambda is equivalent to essentially saying that you previously constructed them. So what's like and maybe now I'll use / for lambda. So then if you do this, so the idea of a lambda term is, is that I'm going to say, these are variables. this next thing is an application. I mean, this is kind of a semantic interpretation, right? This is what this thing means. This thing means apply the lambda term m to the lambda term n. And this one's called an abstraction. This whole thing under here. So there's there's only three syntactic elements in the untyped lambda calculus. So you can encode that in Haskell by saying, okay, we've got a type called lambda, and there's three kinds of elements. There are three different ways of constructing elements of the lambda type. One is by using the constructor var and applying it to a string, and you get back a lambda. And so in the mathematical notation, you're kind of glossing over some stuff, right? You're glossing over the, maybe I should do this too here. You're kind of like glossing over something. Like there's no constructor name for application. You just write things down next to each other. In fact, I mean, in a way, I don't need the parentheses because there's certain conventions that we use. But so now, like, if you do this, this is going to turn out to be the identity function. It's a function that takes an argument, x, and just returns that x. Here's a function that takes two arguments and applies the second argument to the first. And so we can write lots of different functions. Okay. So now a fundamental notion here is free variables. And we can define the function for free variables. I mean, well, here it is. I could do it more mathematically up there, but maybe there's no point. The free variables of a variable are just the singleton containing that variable. Now, maybe I should change the order down here to match the order in the other one. We can do the application in the middle and the abstraction third. Okay. So now let me open a shell and let me start Haskell for a minute. And I can load Lambda. Okay, so now, you can look at like, what is the type of, and you know what? I'm gonna make this simpler. I think I just prefer V for that. It's just shorter to type. I don't know. Where did I must have missed one.
Yep, you missed one. Down where it says abs.
There we go. Yep.
Yep.
Okay. So what's a type of V of Vx? Oh, it's a lambda. What's a type of, you know, whoops, of abs X Vx? That's a lambda. That's the identity function that I just wrote down in that other window. You have to maybe look at the abstraction. I should have maybe looked at these a little closer. App, that's a lambda and that's a lambda by the, you know, the side condition on the construction of this grammar. Abs, well, this is going to be a variable and we're modeling variables as strings, but it's not actually, this is where, like, by turning it into a program, we're observing a little thing that is glossed over in this book, for example, and every place, but mathematicians understand it and don't get upset about it. But there's a difference between this thing here. This doesn't take two lambdas. It takes a variable and a lambda. And so how do we represent variables is by string. So we just put string there. So this is a lambda expression. Does that make sense? Because if I said, for example, here, you know, I said, oh, it doesn't make any sense to put like a lambda where the variable name, the bound variable name is like an application or lambda. It's got to just be a variable. It's just got to be a variable. So the way to restrict that in the data type here is to just use the underlying type of variables. Okay, so now what are the free variables? If you look at this function free variables, it says, look, if I encounter a variable standing on its own, it's free. And so I collect it. If I have an application of T1 to T2, well, you just you collect all the free variables in T1, you know, and I could have called this M and M to match the, you know, I could say M and to sort of match the code there. But, you know, the interesting thing about function application is that in ordinary mathematics, the notation for function application is invisible. You just write down the name of the function and then the arguments. There's no thing that says this is a function application. So here we have to make it explicit by saying we're applying M to N. And now here's the point of the free variables is that when you take a lambda x dot t, you gather all the free variables in T and then you get rid of X. You take X out because X is considered to be bound by this lambda expression in T. So we could try, well, let me say like let, and I say free variables of I. It's got none because the only variable in I is X and it's bound by the lambda. But if I wrote like, Now, what are the free variables of this going to be? There are none. Well, not only are there none, but I did something wrong. Oh, this should be var x. But there are none because we don't include in the free variables, we don't add x into the free variables. If it only occurs there and it doesn't occur in the body of the abstraction, then it's not free. But if we do something like put a z in there, z will be free. Because z is not bound by y and it's not bound by x. Now, something I learned actually from a talk Phil Wadler gave in Edinburgh at a kind of a 50 years of Lambda calculus conference a few years ago was, or no, it was 100 years of Lambda calculus. What am I saying? I think 75 years of Lambda calculus conference. But he pointed out that in Church's original formulation of the Lambda calculus, and somewhere here, it's a little tiny pamphlet that was published by I'm so annoyed. I just saw it yesterday on my desk here. Anyway, it's just this little orange pamphlet published by Princeton University Press. And in the original, Church did not allow, if X occurred bound, it had to occur free in the body. So Church, this was not actually a legal term in the original Lambda calculus, which is, I found that fascinating. I never knew that before. And I think Phil presented it as kind of like, this is something many people don't know. Okay, so then it turns out, though, that if we want to do computation in the system, we do beta reduction. And you do beta reduction when, and now it's probably best to go back here, is, you get something called, so free variables we described, and then readx. A readx is a Lambda term that looks like this. You've got so we've got an application of lambda x dot m to n. Like in our code, this would look like, app abs x, and I'll assume m is some arbitrary term, and then n. So this is how, where m and n are lambda variables ranging over lambda terms. So this thing here, and so how do you compute? Well, this is the ordinary way to compute, but is it really 58? It is. We'll come back to this next time, but you take m, which is the body, and then you replace all, and people write substitution in so many different ways. I happen to like this one because I think it's less confusing. You take the body of the function, and every place there's a free variable x, you replace it by n. But you run it into, and so this here thing is, well, a lambda term of this form, and we say this beta reduces. So this is beta reduction. So this thing here is a readx. It's a lambda term that's an application where the left thing is a abstraction. And it reduces to this, where this denotes a function called capture avoiding substitution. And this is the thing that is so hard to do when you have named variables. And here's the algorithm for doing capture avoiding substitution. And we'll talk about it next time. But the amazing thing is that I'll tell you the story next time. All right. Any questions?
This was good. I learned a lot.
Well, great. Thank you, Philip. I'll put that code up somewhere with the lecture.
That was the thing I was going to ask, is you do put the code up so I can play with it too. But yes.
Yeah. Okay. All right. And we'll go over this some more next time. I'll try to make it a little prettier on some slides. Okay.
So
all right.
Is there a way we can get the slide and then?
Yeah, I'm going to post it to the WIO courses page.
Okay, great, thanks.
You'll see it there. And I don't know, I was trying to contact Philip yesterday. Oh, let me stop recording. I don't need to.